All right, number 4 here we have data in a table about the height of a tree over a 8-year period. First question, part A, is what is h prime of 6? I don't have a function for h, I only have data, and I don't have any data at 6. So the best thing you can do to estimate the derivative at a point is to choose an interval around that point. So you want to do the average rate of change on the interval containing 6. So that ends up being 11 minus 6 over 7 minus 5. We get 5 halves. The second half of this is to interpret the meaning. They're really expecting a sentence here. So something like at t equals 6, the height of the tree is increasing. Growing would be another word there. By, and then 5 halves, and you need units here, it's going to be meters per year. So that's a good summary answer of A. All right, part B says, explain why there's one time where the derivative must be 2. That's the rate of change, must be 2. A lot of the times in a question like this, you are, the mean value theorem is going to help you when you're looking for a slope that equals something. And so if I can find an average rate of change that's equal to 2, the mean value theorem guarantees that I've got an instantaneous rate of change equal to 2. A lot of times the first and last values will give you that average rate of change that you're looking for. But if you think about 15 over 1.5 and 10 minus 2, that doesn't give you 2. So you have to kind of look through the table on this one and figure out, is there an interval where the average rate of change is 2? And you can try some different calculations, but it turns out that the interval from 3 to 5 is the one that is helpful. So if I do h of 5 minus h of 3 over 5 minus 3, I get 6 minus 2 over 5 minus 3, which is 4 halves, which is 2. So by the mean value theorem, since the average rate of change between 3 and 5 equals 2, I know for sure that the derivative must be 2 at least once on the interval from 3 to 5. So again, mean value theorem is the key to this problem. All right, part C asks to figure out the average height of the tree. This is an average value formula. Remember that formula is the integral of the height divided by the interval that you're looking at, all right? So obviously the interval length is 8, but the integral is something I have to figure out, and since I don't have a function for h, I'm going to have to use the table to figure it out. All right, it asks us to do a trapezoidal sum, and so I want to kind of make a trapezoid out of this. I'm going to draw a little quick sketch because it helps me to think about what this graph might look like. So you've got some you've got 2 and 3 and 5 and 7 and 10. Notice that these widths aren't uniform. That's kind of important to notice. And then you've got some increasing heights that look like this. And I basically want to figure out each of these trapezoids one at a time. All right, so remember this is B1 and B2, and this distance is h. And I'm just going to use my trapezoid formula. So in the first one, I'm going to have h over 2, which is 1 half. B1 plus B2 is going to be 1.5 plus 2. In the second one, I have this height, which is 2. 2 over 2 is just 1. And then my two heights, which are 2 and 6. This one also has a width of 2. And my heights are 6 and 11. And this last one has a width of 3. And the heights are 11 and 15. The rest is just some messy math here. This is 3.5, which is 7 halves. I get 7 fourths for that one. The next one is just 8. The next one is just 17. And this last one is 26 times 3 halves. 26 times 1 half is 13. 13 times 3 is 39. So I get 7 fourths plus, this is going to be 25 and 39 is 64. And with a common denominator here, I can get 7 fourths plus 256 fourths. That gives me 263 fourths. That's my integral. And so remember that the average value is going to be 1/8 of that. So 1/8 of that. 263/8 is my final answer here. That is going to be the average height of the tree on the interval from 2 to 10. All right, part D, instead of asking us to use a table, they're now asking us to use a G function to figure out to find the height of the tree. So we're no longer looking at H, we're now looking at G. Reading through this problem, related rates should kind of jump out at you when the tree is 50 meters tall, so that's a height, that's a G value. The diameter of the base of the tree is increasing. The diameter is x, so dx dt is 0.03. And the question is, what is the change in height of the tree at this particular time? Okay? So I want to find dg dt knowing dx dt. I've got a formula that relates g and x, and so I should be able to differentiate this. dg dt is equal to, I need quotient rule here, so it's going to be 100 dx dt. 100 is just the derivative. Oh no, I'm sorry, I do need that. I need 100 dx dt times the bottom, which is 1 plus x. Let me actually go down here a little bit further. So dg dt is 100 dx dt times the bottom, 1 plus x, minus the top, which is 100x, times the derivative of the bottom, which is just dx dt. And that's divided by 1 plus x squared. Right? It doesn't give us an x value, and I've got to plug that in, but it does give us a g value and a g formula. And so over here off to the side, I need to figure out at what x value does g equal 50. So that's a little side problem. 50 plus 50x equals 100x. 50 equals 100x. 50 equals 50x. So x turns out to be 1. So dg dt is going to be the value of this expression when I plug in 1 for x and 0.03 for dx dt. So doing all that, I'm going to get these values, and on the bottom I'm going to get 4. So 0.03 times 100 is just 3, so I have 3 times 2, which is 6. This is minus 3 over 4. 3/4 is your answer. Always a good idea to put units. I don't think it actually requires them, but this is going to be meters per year since it's a rate of change in G.